Okay. All right, sorry about the delay. Any questions before we begin? Okay, well, let's continue from where we left off last time. We were talking about trigonometry. And we talked about the basic trigonometric ratios of sine, cosine, and tangent. We started talking about measuring angles in radians. And so remember, we saw that a full circle, which has 360 degrees, is pi radians. And of course, that means a half circle, which you know is 180 degrees. So that's what's sometimes called a straight angle. This is 2 pi radians. My bad. This is 2 pi radians, and a half circle is going to be pi radians. Now, when you're writing out radians, you don't have to write the word radians. It's not like when you write degrees, you definitely have to put the little symbol for degrees. But if you just put 2 pi or 1 or whatever, when you're measuring angle in radians, it's not necessary to write anything after it. But what it tells you is if you're going from degrees to radians, multiply by pi divided by 180. Pi divided by 180 degrees. And if you're going from radians to degrees, multiply by 180 over pi. So it's easy to go back and forth between radians and degrees in either direction. We'll just do a couple examples right now. So for instance, let's say convert 30 degrees to radians. According to this, if we're going from degrees to radians, we just multiply by 180 by pi over 180. So what we do is we take 30 degrees and multiply by pi divided by 180 degrees. So in other words, we have 30 divided by 180, the 30 on the top, the 180 on the bottom, and then we have our pi. And 30 over 180 is 1/6. So this is 1/6 pi, or pi divided by 6. And if we convert, let's say, pi over, so convert pi over, I don't know, pi over 4 to degrees, it's just as easy. Just take pi over 4 and multiply by 180 over pi. And the pi's cancel out. And we're left with 180 degrees over 4, and that works out to 45 degrees. So it's easy to go back and forth. When you're actually doing computations on your calculator, make sure that your calculator is either set in radians if you mean radians, or degrees if you mean degrees. Any questions before we go on? Okay. So what I want to talk about next, let's see, is that about the edge of where you can see. Yeah, it's about the edge of where you can see. So what I want to talk about next are trigonometric identities. So let me explain what a trigonometric identity is. So trigonometric has to do with trigonometry. That part should be pretty obvious. Has to do with these sines, cosines, tangents, whatever. Identities. An identity is an equality that's true for all values of the variable. It's an equality. True no matter what the variable equals. So let me give you an example of a non-trigonometric identity. How about 2 times x plus 1 equals 2x plus 2? The left side's basically 2x plus 2 once you distribute the 2 in, and the right side's 2x plus 2. If you solve that, you get 0 equals 0, which means it's true no matter what x is. So you know that this is true for all x. This is true for all x. In other words, if you were to solve this, your solution would be all real numbers. That's a non-trigonometric identity. There's no trig functions there, but it's an identity. The left side equals the right side, no matter what the variable equals. So let me give you some trigonometric identities now. So the first one I want to talk about is sometimes called the Pythagorean identity, and I'll explain why in a second. An identity named after Pythagoras. This is probably the best known trigonometric identity. So if theta is the angle, so here theta is the measure of the angle. We'll use the Greek letter theta, then sine squared theta plus cos squared theta equals 1. Now, let me just talk a little bit about notation here. Sine squared theta, when you write it like this, sine squared theta, that's just shorthand for sine theta all squared. Sine theta in parentheses all squared. If I were just to write sine theta and put a square like that, that would not mean the same thing. This does not mean the same as that or that. This means the theta gets squared and then you put it in sine. This says you take sine of the angle first, take sine of your variable first, and then square it. Both of these things mean the same thing, but this doesn't equal either one of them. So this just saves you writing the parentheses around the sign. So you take sine of theta and square it, and you take cosine of theta and then square that. As long as you have the same number here and here, and you add them together, you're going to get 1. Why is that called the Pythagorean identity? Maybe it's obvious to you, or maybe you've seen it before. But if it's not, there's a simple reason. You know that sine, let me just draw a little triangle here, right angle triangle. So ordinarily, it's very easy for me to tell when you're still writing and when I need to slow down. It's a little bit harder right now, partly because a lot of you have your cameras off, and that is your right. You may have your camera off if you feel more comfortable doing so, but it makes it a little bit harder for me to tell when I need to slow down. So I'm going to try to keep my eyes on whoever faces I can actually see. And if you feel comfortable leaving your camera on, I'll ask you to do so. But again, it's up to you to do whatever you want. So why is this called the Pythagorean identity? Well, if I take sine squared theta, we know that's just sine theta all squared, and sine, as you know, is the opposite over the hypotenuse. So sine squared theta is the opposite over hypotenuse all squared. And cos squared theta, you know, cosine is the adjacent over the hypotenuse. So this is the adjacent over the hypotenuse, all squared. So sine, oops, I don't know why I put parentheses around that. Not that they hurt, but they're not necessary. So sine squared theta plus cos squared theta. The sine is just the opposite over hypotenuse, and that's squared. And cosine is the adjacent over hypotenuse, and that's squared. And if we do the square, we know when we square fractions, just square the top and square the bottom. So this is the opposite squared over the hypotenuse squared. And this is the adjacent squared over the hypotenuse squared. A little bit of algebra there. And we know that when you add fractions, you just get a common denominator. Well, they already have a common denominator, so this is going to be over hypotenuse squared. We just take the opposite squared plus the adjacent squared. But by the Pythagorean theorem, the opposite squared plus the adjacent squared is the hypotenuse squared. A squared plus b squared equals c squared. So what we have here is just the hypotenuse squared over the hypotenuse squared. That equals 1, just like we said it was. Sine squared plus cos squared equals 1. This is just the Pythagorean theorem in disguise. That's all that sine squared plus cos squared equals 1 is all about. So if you start off with sine squared plus cos squared equals 1, you get a couple more trig identities almost for free. So let me just start off with sine squared plus cos squared equals 1. And I happen to be using theta here. You don't have to use theta. You could use x, you could use y, you could use any variable. Sine squared x plus cos squared x equals 1, and so on. As long as whatever is there is the same thing as whatever is there. What I'm going to do is take everything here, divide both sides of the equation by cos squared x. Sorry, cos squared theta. I'm using theta right now. Well, sine over cos, that's just tangent. Cos over cos is 1. And 1 over cosine is known as secant. So this is secant squared. So 1 over cosine is known as secant. So tan squared plus 1 equals secant squared theta. There's another well-known trig identity. So let me just put some boxes around these things. I could just as easily go through and divide all sides of the equation by sine squared theta, and I'd end up with something else involving something called cotangent and cosecant. We're not going to need that this semester, so I'm not going to do it. For those of you moving on into Calculus 2 in one semester, you will need that, but you'll probably review that when you go into Calculus 2. But I do want to talk about a couple more trig identities that we will need this semester, and that is the sine and cosine addition formulas. So I'm going to switch from thetas now to x's and y's, just because I don't want to introduce another Greek letter right now. So sine of x plus y, theta plus mu, if you really love these Greek letters, you can use 2 Greek letters. I'll just use 2 Roman letters. Sine of x plus y equals sine x cosine y plus cos x times sine y. So sine of x plus y is sine x times cosine y plus cos x times sine y. That's called the sine addition formula. And for those of you who would like to see a proof of that, I'm not going to do a proof of that in this course. I'm not going to work through the proof, but there's a really slick proof that's basically just one picture. And if you just look up the sine addition formula on Wikipedia, it pops right up at the right-hand side of the page. It's a really, I think it's the nicest proof I've ever seen. It's just one little picture, and you can see why sine x plus y equals sine x cos y plus cos x sine y. If I were to put a minus sign right here, then it's the same formula, except there's a minus sign right there. So there's like two formulas in one with plus sign, one with minus sign. And there is a similar formula, or similar pair of formulas for cosine. Cosine of x plus y. We have to be a little careful here. This is cos x, cos y, so the coses go together. And if there's a plus sign here, we get a minus sign here. Like before, if there was a plus, there was a plus. Now the plus goes with a minus. Sine x, sine y. So there's a minus sign here. Unsurprisingly, this changes to a plus. So for sine, use the same sign. Not trying to be funny there, but for sine, if it's a plus, use a plus, and if it's a minus, use a minus. And for cosine, if it's a plus, use a minus, and if it's minus, use a plus. And of course, the sines and the cosines are in slightly different places. That is all we really have to know about trigonometry this semester. Well, not quite, but that's all we have to know about trigonometry and triangles this semester. We're going to talk a little bit more about trig functions, but we'll do that in a little while. Okay, let's move on to exponents and logarithms. Exponents and logarithms. And let's just talk about the exponentiation rules. So how about this? Let's start off with, there's no particular order for these. Let's start off with a to the x times a to the y equals a to the x plus y. When you multiply powers, you add exponents. That's something that you probably should know well. That should make total sense to you. If I take the number 5 and square it and multiply it by 5 cubed, this is nothing more than 5 times 5. And this is nothing more than 5 times 5 times 5. Let me put parentheses around that. 5 times 5, and this is 5 times 5 times 5. And if you multiply that all together, you end up with 5 times 5 times 5 times 5 times 5. In other words, 5 to the 5th, or 5 to the 2 plus 3. So at least for whole number values of the exponent, this should make complete sense. It should be intuitive. Really, the more that's intuitive, the less you have to memorize, in my opinion, the better. It's easier, it's more, the knowledge is more robust. So similarly, if I take a to the x and divide by a to the y, when you divide powers, you subtract exponents. This, again, is not something you have to memorize. That should make sense. So if I take, let's say I take 7 to the power 5 and divide by 7 squared, I have 7 times 7 times 7 times 7 times 7 on top, and I have 2 of them on the bottom. So 5 sevens multiplied together on top, and 2 sevens multiplied together on the bottom. Well, 2 of these cancel out with 2 of those, and so I'm left with 7 cubed, or 7 to the 5 minus 2. So these rules should completely make sense to you. If you believe that, you have to believe that a to the 0 is equal to 1. Because if I have something like, let's say I have a cubed divided by a cubed. According to what I just did, that's a to the 3 minus 3, or a to the 0. But anything divided by itself is equal to 1. So if you believe rule number 2, you have to believe rule number 3. So again, it's not something that you really have to memorize. Let's do this. A to the x to the y. The famous taking a power to a power. When you take a power to a power, you'll recall that you multiply exponents. A to the x to the y is just a to the x times y. And again, that should make intuitive sense. If I have something like 7 squared cubed, this is just 7 times 7 cubed. And when you cube something, you just multiply it by itself 3 times. So it's 7 times 7, 7 times 7, 7 times 7. Well, there are 1, 2, 3, 4, 5, 6 sevens. Of course there are 6 sevens, because you had 2, and then you have 3 groups of those. So 2 times 3 is 6. So this is 7 to the 6, which is just 7 to the 2 times 3. How are we doing here? Not bad. AB to the power x. When you have a product to a power, the power distributes over the product. This is a to the x times b to the x. So for instance, if I have, oh, why did I put that in parentheses? So if I have, let's say 5 times 7 all cubed, this is 5 times 7, 5 times 7, 5 times 7. We can group the 5s. This is 5 times 5 times 5. We can group the 7s, 7 times 7 times 7, and this is 5 cubed times 7 cubed. So again, it should make intuitive sense that exponentiation distributes over multiplication. And there's a corresponding rule for division. A divided by b to the x, for the same reason, is a to the x over b to the x. So we know that exponentiation distributes over both multiplication and over division. I want to talk about one common algebraic mistake that people make, especially if they're in a hurry. Exponentiation does not distribute over either addition or subtraction. I truly do not mean to insult your intelligence here. It's possible you never do this, but it happens so frequently that I think it's better safe than sorry for me to mention this. So if I take, x plus y, oops, let me say a plus b, and square it, that does not equal a squared plus b squared. This is not the same as a squared plus b squared. You can't just take that square and put it over the a and take the square and put it over the b and everything is wonderful. You know how to square this. So a plus b squared is a plus b times a plus b, and you have to FOIL this all out. A squared plus AB plus another AB, that's 2AB plus B squared. And I think everybody, by the time they get to calculus, knows that, but sometimes in a hurry, there's pressure, we're trying to get through a problem, and we have a limited amount of time, and it's a common mistake that happens, so try to make sure it doesn't happen to you. If I had something like a plus b cubed, it's not a cubed plus b cubed, it's a plus b times a plus b. You'd multiply these first two out, you get what we got here. That's a squared plus 2ab plus b squared. And then you'd have to take all that and multiply by a plus b. And what you get ultimately is a cubed plus 3a squared b plus 3ab squared plus b cubed once you collect up all like terms. There's a line or two that I didn't do the algebra. I just sort of jumped from the answer and can collect up all, and show you the stuff where you collect up like terms. But it's algebra, and hopefully that is something that you could do and work out the details. And if it's not, please feel free to ask. So exponentiation does not distribute over addition or subtraction. It does very nicely distribute over multiplication and division. Okay. So where was I? 1, 2, 3, 4. What was the last rule, number 5? Or was it 6? It was 6,
Number
right?
6.
6. Okay, so 7. So 7, a to the minus x is equal to 1 divided by a to the x. And again, if you believe rule number 2, you got to believe this, because a to the minus x is the same as a to the 0 minus x. And we already know that when you subtract exponents, that's the same as dividing powers. This is a to the 0 divided by a to the x. And if you believe rule number 3, a to the 0, I think it was rule number 3, a to the 0 was 1, and this is a to the x. So it makes sense that a to the minus x is 1 over a to the x. I'm not sort of stating anything that you couldn't work out yourself based on the previous rules. A to the 1/2 is equal to the square root of a. At least they're close enough that we will consider them the same for now. Technically, they're a little bit different because this symbol, so let me just tell you that I fibbed just slightly here. Let me say this is almost. This symbol here, the radical, technically means positive square root. So if I write root 4, that's the number 2. It's not plus or minus 2. Root 4 equals 2. That's why if you mean plus or minus 2, you have to put a plus or minus before the square root of 4. You have to write it in yourself. So this symbol technically means positive square root. And a to the 1 over n is the nth root. Of a. Like a to the 1/3 is the cubed root of a to the 1/4 is the 4th root of a, and so on. So like 8 to the 1/3 is the cubed root of 8. And we're looking for a number that you multiply by itself 3 times to get 8. Well, that's the number 2. That's pretty much it for exponentiation. Are there any questions before we move on? All right. Well, let's move on to logarithms then. If you understand exponentiation, there is absolutely no reason that logarithms can't be totally clear to you. We read this as log of a to the base b, or log base b of a. So or you can just as easily say log base b of a. It doesn't matter which order you put it in, as long as the base goes in front of the b. And log base b of a equals x means that b to the x, let's write it over here, equals a. These two things are synonyms. Log base b of a equals x means b to the x equals a. So in other words, log base b of a is the number you have to raise b to get a. It's the number you have to raise b to get a. That's all a logarithm is. And we'll do a bunch of examples. Let's start with that. Log base 2 of the number 8. What number do you have to raise 2 to get 8?
3.
3, right. Log base 2 of 8 is 3, since 2 cubed is 2 times 2 times 2, 8. So when you try to compute log base something of this, well, log base a of b, just ask yourself, what power do you have to raise that to get that? That's all a logarithm is. It's exponentiation in reverse. How about this? Log base 2 of the number, oh, let's say 32. How many 2's do you have to multiply together to get 32? You might have to count them on your fingers. Right. Right. So CJ had 5 fingers up. So 2 times 2 is 4, times 2 is 8, times 2 is 16, 16 times 2 is 32. 5, 2. If you multiply 2 together 5 times, you get 32. So this is 5. Since 2 to the 5th equals 32. Let's keep doing some more. How about log base 2 of the number 1? What power do you raise 2 to get the number 1? What power do you raise anything to get the number 1?
0.
Yeah, 0, exactly. See some of you making zeros with your hands, right? Because 2 to the 0, we know that something raised to the power 0 is equal to 1. I think that was rule number 3. How about this? So far I've done a bunch of log base 2's. I think I'll stick with that just a little bit longer. How about log base 2 of 1/8? 1/8, 0.125. What power do you raise 2 to get 1/8?
1/3.
What was that?
1/3.
It's not 1/3. If you take 2 to the 1/3, that's the cube root of 2. So you can look at your exponentiation rules.
Minus 3.
Minus what?
Minus 3.
Minus 3, right. Because 2 to the minus 3 is the same as 1/2 cubed. In other words, 1/8. How about log base 10 of, oh, let's say 1,000,000?
Six.
It's 6, right? because 10 to the 6th is a million. Raising 10 to numbers, at least raising it to positive whole numbers, is easy. All you do is you put down a 1 and then this many number of zeros. 1, 2, 3, 4, 5, 6. We tend to group them in threes. So log base 10 of a million is 6 because 10 to the 6th is a million. How about log base 10 of the number 0.001?
-3.
Good, it's -3. So yeah, this is -3 because 10 to the -3 is 1 over 10 cubed, which is 0.001. 1/1000th. So 1/10, 1/100th, 1/1000th. How about this? Log base 10 of the number 10 to the power 100. That's right. It's 100. If that's not clear to you, try to unwrap it in words. What we have to do here is figure out what power you have to raise 10 to get 10 raised to the power 100. What power do you raise 10 to get 10 to raise to the power 100? Well, 100, of course. 10 raised to the power 100 is equal to 10 raised to the power 100. So this is 100. Because 10 raised to the power 100 equals 10 raised to the power 100. By the way, this number right here, this is, as we said over here, 10 to the 6th was a 1 followed by 6 zeros. This is a 1 followed by 100 zeros. That number, just for cultural reference, has a name. That's called 1 G-O-O-G-O-L, 1 Google. And it's huge. I mean, 10 raised to the power 100, 1 with 100 zeros is an incredibly big number. To put it in perspective, the number of atoms in the number of in the entire visible universe, all the galaxies, all the planets, all the stars that we can see in the sky, is usually estimated at somewhere between 10 to the 75th and 10 to the 87th. That's the number of atoms in the whole visible universe. All the universe we know is there. So this is much bigger than that. It's an incredibly huge number. There is a story, I'm not 100% sure this story is true, that when the two founders of Google founded their company, they tried to call it G-O-O-G-O-L. The idea was that their search engine would search a lot of pages, not that many because that's bigger than the number of atoms in the visible universe, but a lot. And the first person that wrote them a check to fund their company misspelled it G-O-O-G-L-E, and hence we type G-O-O-G-L-E instead of G-O-O-G-O-L. Okay, how are we doing? About 3 minutes. Log base 10 of 50. That's not, unless you're some sort of computational, prodigy, that's not something that you can do in your head because it's not a whole number. 10 raised to no whole number is 50. But at least in your head, you should be able to say it's between this whole number and this whole number. What two whole numbers is log base 10 of 50 between? So what powers of 10 is 50 between?
7.
What was that?
7.
7? No. So what? So give me a power of 10 that's smaller than 50. So 50.
10 raised to 1 and 10 raised to 2.
Yeah, right. 50 is between 10, which is 10 to the raised to the power 1, and 100, which is 10 raised to the power 2. So log base 10 of 50, you know right away, is going to be between 1 and 2. Because taking 10 and squaring, it's too big. Taking 10 and raising it to the first power is too small. So even though you won't be able to do this in your head, you can plug this into your calculator and get a value. You can still estimate it between 1 and 2. Let's see. Log base 2 of the number 10. What whole numbers is that between? So 10 is between what powers of 2?
3 and 4.
One and 2.
Well, 2 raised to the power 1 is 2, and 2 raised to the power 2 is 4. Those are both smaller than 10.
2 and 3.
Well, 2 raised to the power 2 is 4, and 2 raised to the power 3 is 8. Those are still both smaller than 10. But this is certainly bigger than 8, and that's 2 cubed. What's the next power of 2?
4.
Yeah, 2 to the 4th, which is 16. 2 times 2 times 2 times 2 is 16. So this is between 3 and 4. So even though we won't be able to compute it, if you type this into your calculator, you will see that you get some number between 3 and 4. And I will teach you next time how to put this into your calculator depending on what your calculator looks like. Some of you have different buttons on your calculator, and we'll talk about that. Are there any questions? All right, we'll pick it up here next time. I will see you all on Friday.